Let's see. You all are teachers, so you might appreciate this. It's quiz time. What's NDVI?
Something variable index.
Have you all heard that term before today, ever?
No.
Oh, you haven't? All right. Well, if you start listening to people talk about precision agriculture, remote sensing, you're going to hear the word NDVI tossed around a lot, and vegetation indices. Since NDVI is the most popularly used vegetation index, I'm just going to give you all kind of a better intuition for it than you might have already, right? So, just to review a few things, this is the electromagnetic spectrum, and if you see these little rectangles I drew around these regions of the spectrum, what these are wave bands. So this is wavelength. As you move from left to right, wavelength gets longer, but there are wave bands that our instruments detect in, and those wave bands can be broad, like this near-infrared one over here, or it could be narrow, such as the blue one. But that's how we get data. And so however intense the electromagnetic radiation is within one of those wave bands, that's going to correspond to how large of a quantity we get back in our data for that, all right? So we're sensing in specific regions of the spectrum. And there was a question earlier about wavelength. Was your question about wave band width or about wavelength being better, shorter being better?
Just how it's read. I mean, the different change.
Oh, how it's read. Yeah. Well, basically, the width. It's the width of the band you're using that's really important. Sometimes there are broad absorption features and sometimes they're narrow. If you have a narrow absorption feature and you're using a broad bandwidth, it's going to average over that and you're going to miss out on what you're looking for. All right, so let's move on. All right, so here is a reflectance spectrum for a healthy leaf that I went out in the field and I measured this using a really nerdy tool we have called a spectroradiometer. It just measures light across the spectrum, and light is the radiance or intensity of light. And right here, if you see this bar going down, this red bar and this black bar, what this is, that's at about 670 nanometers. That's where there's chlorophyll absorption. All right, so that's what's going on there. Right up here, this is near-infrared light. Plants don't absorb near-infrared light right there. Does anyone know why? More quiz questions. Anyone? Well, if they did absorb that, they would have a lot harder time cooling themselves down, wouldn't they? Right? But also, there's not enough energy here to initiate the electron transitions needed for photosynthesis. Right? So if you have a healthy plant leaf, right, such as this green leaf that I have right here, what you're going to have is a lot of red absorption and very little near-infrared absorption. So low red reflectance, high near-infrared reflectance. All right, and so this little spike right here, see how there's a little broad peak right there? Plants do absorb green light, just not nearly as much green light as they do red or blue light, right? And so that's why they appear green to us. All right, so let's move on and see what a not so healthy leaf looks like. All right, this leaf is yellow. And yellow is a combination of what two? It's two colors mixing together. What is it? Come on, teachers.
Red and yellow.
Red and green, right?
Green.
Yeah, and then those make yellow. So you can see right here, 550 nanometers and 650, that's green and red. And then there's very little blue reflectance. So what you have here is you've got high green, high red reflectance, low blue, and so that gives us yellow, right? Now this high red reflectance is because the chlorophyll isn't absorbing that red light because the plant tissue isn't healthy. It might not have enough nitrogen. But anyway, so you can see that difference in the curve. If this was a healthy leaf, then there'd be a lot more absorption going on right here, but it's not. And so NDVI, let's get back to this NDVI term that you might hear a lot over the next day. All it is, as Dr. Long said, it's just a ratio of dividing red into near-infrared. That's really all it is fundamentally. And you can see right here in this unhealthy leaf, if you divided this reflectance value, which is about 0.5, into this one over here, which is about 0.52, you take those in ratio, would that be a very big number? No. So would you need to fertilize? Probably. Right, but if we go back over here, look at a ratio here of 0.1 into 0.7. You get a bigger number back, right? And so what we're doing is we're using information that's in part of the electromagnetic spectrum that we can't see with our eyes, but our instruments can. since these instruments that we have, like this camera on the octochopter over there, we can use these as tools to help us better manage our land, farmland. All right, so let's look at some more spectra. So that's a chlorotic leaf. Here's a dead leaf. It's brown. All right, now if you were just looking at the red wave band, it looks pretty similar to the healthy leaf, doesn't it? There's a lot of red light that's, or not a lot of red lights being reflected off. But here's where NDVI comes to the rescue. Well, it sees this near-infrared reflectance. That's very low. You take those in ratio, again, you know it's not healthy. If you're just working with red light, you wouldn't be able to get this type of information. This is the basic premise for any spectral index that we use for remote sensing in agriculture. There's something going on in one band, and that's where the action's at. Then there's another band that we use in combination with that. And using the two together, or sometimes three, we can find out a lot more about what's happening health-wise. All right, so that's a brown leaf. And you can see since it's brown, pretty much across the whole spectrum, it's not reflecting very much, right? So it's darker, kind of a muddled color. All right, so this is just a sheet of Teflon that I took the readings on top of. And this was my field assistant that day, Mandy. She's really good. She's really good. And so what I did next is I took a reflectance spectrum of her forearm. And that's what your skin looks like. That's basically what, well, someone with light colored skin like Mandy has. And that's her hand, just so you know for reference. And so you can see from here, she basically looks like a very unhealthy plant leaf. Right? And so if you were to calculate NDVI for Mandy, she'd have a very low, pardon me?
So there was not a lot of photosynthesis.
No, not hardly any. She's not photoautotrophic. She's heterotrophic. So, so anyway, if you took a ratio of red to near-infrared light, you wouldn't get a really high value back, which is what you would expect, again, because she's heterotrophic. Even though she is really earthy, she doesn't have much chlorophyll, or hardly any. All right, so that's what that shows. So that's the human skin. All right, so how does this impact the research that I'm doing? I work with canola, right? Canola is an oilseed crop. It's not under as much area, there's not as much area under canola cultivation as there is for other crops like wheat, corn, and soybeans. But it is really big in Canada, and the land under cultivation keeps increasing rapidly from year to year. So we're looking at it. It's very important. I found this magazine news article. It was an online magazine from Canada called The Western Producer. All of their satellite yield estimates for canola are too low. It says satellite crop estimate too low, says analysts. They don't know what's going on. Why is this happening? Well, here's NDVI again. And what you can see in this picture, here's a plant with green leaves, and this one has brown leaves. This healthy leaf is reflecting 50% of the light that's on it, and it's only of the near-infrared light, and it's reflecting 8% of the visible light, right? So if you go through that calculation, you end up with 0.72, which is a high number. This is just a review. All right. Now this unhealthy plant, it's only reflecting 40% of the near-infrared light, but it's also reflecting 30% of the red visible light. So you plug that into NDVI and you get 0.14. All right, that's all and fine for crops that are mostly leaf, where most of the signal that your device is detecting is coming from the leaves. Now, here's a picture. This is an oblique image of canola. So can you see anything in this canola canopy besides leaves? Flowers, right? And so flowers are yellow, and yellow is what two wave bands? Or not wave, yeah, what two wave bands are they? Red and green. And which one of those two is used in NDVI? Red, right? So you see a problem coming up if you're doing remote sensing of canola and you're using NDVI. See, the Canadian analysts are using NDVI, and they don't know any better. Right? They will soon enough. Soon enough. All right, so, pardon me? Yeah, metrics. NDVI, well, so plants aren't always in the same development stages. Canola, is canola always flowering? Is it always yellow? Are people always getting their wedding pictures taken in it? No, they've got a narrow time. It just so happens that if you use NDVI while canola is flowering, it's a problem. But there's other development stages, such as when it's in its rosette, its bud, and after the flowers fall off in ripening, it performs just fine. But say you're monitoring canola over the course of the growing season and you have, I don't know, 4 satellite images. Say you get one at rosette, 1 satellite image at bud, 1 at flower, 1 at ripening. If you average the NDVI from all of those together to try to get what's called an integrated yield response, the values taken from during flowering are going to throw everything off, because NDVI is saying these plants aren't very healthy, right? Where in reality they are really healthy if there's a lot of flowering going on out there. So how do we get around this? How do we work around that? Here's a reflectance spectrum for soil. Just so you know what soil looks like, that's this red line. And then this green line here is petal. And then right here is blue and this is yellow. So you can see the petals are very strong yellow. But here is a canola canopy for 10% flowers and 90% leaves. You can see that it still has a lot of red absorption. But when there's 50% flowers and 50% leaves, you see this red jump up a lot, right? So the more and more flowers corresponds to the more and more red reflectance, which means even though the chlorophyll, and chlorophyll is on this axis here, even though the chlorophyll is staying the same, your estimate of it's decreasing. That's the impact that it has. And that's why the satellite yield estimates are too low, right? All right, so what NDVI is it senses vegetative growth in a canopy, right? And it's a vegetation index. Now what we decided to do was, instead of near infrared and red, look at the ratio of blue to green, right? Because it's flowers. There are flowers there, right? They're reflecting green light, they're reflecting red light, but they're not reflecting blue. It's actually their carotenoids in the flower tissue that are absorbing blue light, and that's why they look yellow, right? So if from a satellite sensor that's, say, 400 feet in the air, a pixel is going to correspond, well, from that thing to, a few centimeters. That's going to be averaging the intensity of, I don't know, maybe a few hundred flowers. So if you take a ratio of blue, where there's no absorption, to green, that's just half a yellow, but it's enough to work with, right? Look at this blue to green here. See how green's a lot higher? The more green reflectance relative to blue corresponds to the more flowers that are within the pixel's field of view, right? And so where we have more flowers, there's going to be more pods, because that's what's the next step. About half of the flowers are going to start producing pods with seeds in them, right? More pods, more seeds. So that's how we get to yield. Instead of looking at leaves as an indicator for what yield's going to be, we just say how many flowers are out there. The more flowers, the more yield. And if you look at this, the way that we formulate it, if you do a normalized difference version of it, or you just divide blue into green, it works out basically the same when you do the statistics. But what this is, what we're calling it, since it's sensing reproductive growth and not vegetative growth, we're calling it, well, I don't know how well this is going to fly, a reproductive index, right? It's more closely linked to what the final yield is than a leaf, at least for this crop, right? And so what we did last summer is we went out on 4 dates. This was when the canola was bolting, but before flowering. This is just at anthesis when flowering started. This is full flower, June 27th, and then this is ripening, when most of the flowers had fallen off. On these dates, I went around and I sampled about 88 portions of the field. So I had 88 sample points, and I used an instrument. It's a handheld instrument, and it basically lets me see everything that's happening across the spectrum. And I can convert that into red, green, blue, wave bands, and infrared. So what I did for each of these dates was I calculated NDVI and the yellowness index, the index that I described that tells you how yellow something is, which is just a blue-green ratio. And then what we did is we related that to the final yield, pounds of seed, for each of those sample points that I measured at. And we decided to see, put the two head-to-head. Which one predicts yield better? Does one underestimate yield? Is one closer? Right? And this graph doesn't show up very big on here, but this is NDVI, and this is showing the R squared for each one of those sampling dates. R squared is just a number that tells you how strong is a relationship, right? If you have an R squared of 1, it's great, right? If you get an R squared in practice of what we do, 0.8, I think that's phenomenal. Realistically, it ends up somewhere between like 0.3 and 0.6. But anyway, so for that first date, right, during bolting, the R squared is 0.45 for NDVI. Right at anthesis, right before there's many flowers out there, there's a lot more leaf matter, the NDVI's R squared is 0.53. At full flower, it drops down to 0.23. right? And then at maturity, it jumps back up to 0.53. So you can see at full flower, the relationship really breaks down. The scatter doesn't look nearly as good, and the R-squared value is really low. So what the Canadian remote sensing analysts are doing is, well, I haven't spoken with them about it. Well, I spoke with one. What they're doing is they're averaging that full flower one in there, and that's very low. You can see all these values here below that line. It's all underestimating, so they're getting underestimates. So if you're working with just one satellite image during flowering, you're going to be way off base, way off base. So let's look at what the yellowness index. So for that first date, it's 0.47, anthesis 0.64, 0.64, and then it stayed up there. If you look at the scatter, see how the scatter forms a nice line? That means that yellowness has a linear relationship, a very easy to understand predictive relationship with yield. Let's go back to here again. You can see a lot of the points are way too low, right? Again, that's because that red increase reduces the NDVI value, right? And so that's the basis of what we're doing. I've done this with satellite-based data for county-level yield data for North Dakota. Same relationship holds. So I've looked at this with different sensor systems and at different scales with different data suppliers. And so far this seems to be pretty solid. So that's what we're doing with that. We also have an algorithm that I wrote that'll take in a satellite image and just tell us how many acres of canola are under production within the satellite's field of view. And so that's pretty cool too. That's good for the people that procure the seed for the crushing facilities, because they like to know where is it and how much of it is there. That helps them estimate, do I need a source from other locations, or can I get most of my stuff from here or there? So that's what we're doing with remote sensing in canola. Now again, what's NDVI? Red to near, that's all it is. The formula looks a little confusing, maybe. You know, there's a subtraction and then there's an addition underneath it or whatever. All it is fundamentally is just dividing red into near infrared light. Does that always work for every plant at every development stage? No. Does it work for Mandy to tell how healthy she is? No. So when we have these different indices, you have to be careful about what are you applying it to and when. Because you'll actually be indexing something besides vegetation if you're pointing it at non-vegetation or if it's the wrong development stage. All right? Are there any questions?
Okay, I have a question. So, trying to look at the yellow spectrum now, like with this reproductive index, right?
Well, what we're looking at is
Blue.
yellow is a mixture of red and green, right? Let me just go back to, I'll use this one. So if it's yellow, see how there's more?
Okay, so I guess my question is, if a leaf is unhealthy, it will be yellow.
Mm-hmm.
And if a flower is healthy, it will be yellow.
Right.
So how can you tell the difference?
Near infrared reflectance too.
Okay.
You can throw that in.
Okay.
Right.
Is that
You
what you do?
aren't limited to just two, right? But also the magnitude of the response in the yellow. But here's the other big difference is, and this is why I do a ratio of blue to green and not blue to red, because even though there's yellow reflectance that gets attenuated, not yellow reflectance, even though there's red reflectance from a yellow leaf, that gets attenuated by the red absorption from the chlorophyll. By doing green instead of red, we're not getting mixed up by that red absorption.
Okay.
And so we have more dynamic range. Right, but also, typically during flowering, there aren't yellow leaves at that development stage. So I wouldn't use the yellowness index at an earlier development stage, such as rosette, when you would top dress and do a split fertilizer application. I wouldn't use that then. I'd use something, a red edge index or NDVI, right? Because then you're getting yellowness because of nitrogen deficiency. So again, you got to really think about what's the development stage, what's happening, and then which index to use. So that's a really good question. There's yellow happening, but there's a different mechanism, right? Because for the chlorotic leaf, that's just a lack of red absorption. For the flowering case, there's tons of red absorption, right? But there's tons of red reflectance, so they're mixing together. And if you look at a plot, well, there's the reflectance of a flower. Let's see where this is peaking up at. I can't read it on this PDF, but it's a lot higher than a chlorotic leaf.
Okay.
It's a lot higher. So you can just look at the magnitude of the reflectance values as well. Yeah.
So can this technology be used on a standard pivot to evaluate how much water needs to be applied to the plant? Because, plant changes based on water content.
Right.
If it's too
Yeah.
wet, it's yellow. If it's too dry, it gets darker.
I would use thermal infrared for that, right? Because that's looking at water. That'd be pretty close to, the more water there is, it's going to be cooler on a thermal image. So, right? So those are going to be all your wet spots. All the bright spots on a thermal image, that's where it's going to be hotter, right? And so that'd be the quickest, easiest way to get at moisture. There's also a moisture water absorption band at about, was it 1250 nanometers? A nano means a billionth of a meter. It's a very small wavelength. But there's water absorption there. So you could look at a ratio of that band with something else if you had the right sensor. Typically looking at water and knowing that you're nailing water directly and not something else that's just related to water, you got to go into longer wavelengths than visible and the near infrared, up into maybe the shortwave infrared, or ideally you'd have a thermal